Unit 2 is all about rational functions. And in section 12.2, we're going to graph these rational functions. So by definition, a rational function is a function whose rule is a quotient of polynomials in which the denominator has a degree of at least 1. So remember, quotient means division, and the denominator, or the bottom part, has to have a degree of at least 1. So that means that there must be a variable in the denominator. There has to be at least 1 for it to be considered a rational function. So here's some examples. This first one right here is one that we did yesterday, the inverse variation. And then the other ones are just other examples of rational functions where we have a variable, in this case x, in the denominator. So because we're putting x's, numbers we don't know in the denominator, we need to remember a rule. We can never divide by 0. Ever, ever, ever. If there was just a number in the denominator, we would know that it is never 0. It's that number. But because we have an x, because we have a variable, we have things called excluded values. So for any function involving x and y, an excluded value is any x value that makes the function of y undefined. So for a rational function, an excluded value is any value that makes the denominator equal to 0. So this first one right here, what number would make the denominator equal to 0? Well, since x is the only number under there, we can't have x equals 0. Not possible, because if I plug this in, 2 divided by 0, this would be undefined. It would make your y value undefined, and that can't happen. So our excluded value is 0, not allowed. For problem B, it's a little more work. Hopefully most people can just recognize right away that 2 would be the value that's excluded. But if you can't, or when the problems start to get a little harder, what you can do is set the denominator not equal to 0, because we don't want that to happen. And then you solve. So we would add 2 to both sides, and we get the x can't be 2. If x is 2, that would make our denominator 0, which can't happen. Any other number will work, positive or negative. Even the number 0 will work here, because if I do 6 over 0 minus 2, I end up with this, which is totally possible. So 2 is the only value that that x cannot be. So now let's talk about the graphs, and then we'll get back to those excluded values and what those mean for our graph. So this first one was very similar to one that we did yesterday with the inverse variation. And in this case, our k would be 1. And we see that it does exactly what our graph did yesterday. It makes 2 smooth curves in quadrants 1 and 3. And now let's move this graph around a little bit and see what happens. If I look at the equation y equals 1 divided by x minus 3, we see that our graph shifted. It's now here and here. So we can see that it shifted over 3 spaces. Remember, it used to be around here that the 2 lines got really close to. But now, this one they're still getting pretty close to, but it moved to positive 3. So keep that in mind with how that affects the x minus 3 in the denominator. And then how about this next one here? Not only does this part move to 3, but we have it shifted up. Our 2 curves now go up to 2. And we can see a 2 in our equation, x minus 3 and then plus a 2. So those lines that I made are something called asymptotes. So most rational functions are discontinuous. That means you can't draw the whole graph without picking up your pencil. So this graph, I can draw this part, but then I have to pick up my pencil to draw this part. Not continuous. meaning that their graph contains one or more jumps, breaks, or holes. This always occurs at an excluded value, the ones that we were just talking about. So one place that a graph of a rational function is discontinuous is at an asymptote. Asymptote. An asymptote is a line. And it's a line that the graph gets really, 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 really close to, but never touches. So in this graph here, the two axes, this line right here and this line right here, are lines that our graph gets really, really, really super close to. We can see it's getting closer here and getting closer down here, but it's never going to touch those lines, and it's also never going to cross those lines. Same thing here. It's going to get really close and really close, but never touch or cross. So we can find the asymptotes by just taking a look at our equations. So for rational functions, your vertical asymptotes will occur at the excluded values. Remember, vertical are up and down. They have equations like x equals a number. So those are our excluded values. So if we have the most basic function, y equals 1 over x, the denominator can't be 0. We can't have x equals 0, so 0 is an excluded value. So that means that this line right here, x equals 0, or the vertical line here, can't be 0. That is one of our asymptotes. Our graph will never cross that. And then it also has a horizontal asymptote, or ones that go this way, that have equations y equals a number, when y equals 0. And that's because it doesn't matter what number I plug into this equation for x, I will never get 0. 1 divided by a really, really, really big number won't give me 0. 1 divided by a really, really, really small number won't give me 0. There's nothing that I can plug in that will give me y equals 0. So that means your graph can never cross this horizontal line either. So now let's look at that one that we shifted, the graph of y equals 1 over x minus 3 plus 2. So we already drew the asymptotes on here where we thought they were, but now let's make sense of the equation. So remember this x minus 3 part right here made it go 3 units to the right. So now instead of being at x equals 0, the thing that x can't be is 3. X cannot be 3. That's our excluded value. So because of that, that's our equation for the asymptote. X equals 3. It's going to get really, really close to that, but never touch it. And then we noticed that this plus 2 part of our equation moved all the y values over. So it moved them up 2 spaces. So now there's nothing that I could plug into my equation to get out 2 for y. Absolutely nothing. Because in order for that to happen, this whole value would have to equal 0 here, and we know that can't happen. So y can never be 2. Those are our 2 asymptotes. So, identifying asymptotes. Here's some examples. If you have a rational function that looks like this, to figure out your vertical asymptote, the x equals, the one that goes up and down, you find your excluded value. Or you take this stuff and you solve for x. And that is your vertical asymptote. This number that's being added or subtracted right here is always your horizontal asymptote. So let's find the asymptotes of these 2 functions. The very first one has this in the denominator. So hopefully everybody can see here, the excluded value is negative 7. But remember what you're doing is you're setting this equal to 0 and you're solving for x. What number would give me 0 there? So if I subtract 7, I get x equals negative 7. That is one of my asymptotes. X can never equal negative 7 in my equation. And then if I want to find my horizontal asymptote, I look at whatever number is being added or subtracted on the end. Since we have nothing, there's really like a plus 0 there. So that is my horizontal asymptote, y equals 0. Remember, these are things that our equation can never equal. We can never plug in x equals negative 7, and we can never get out 0 for y. So that's why when we go to graph them, our graph is going to get really, really close to them, but never touch. So try the next one on your own. Pause the video. So you should have asymptotes at x equals 3 halves and one at y equals 8. It's not just enough to tell me 3 halves and 8. They need to be equations because remember, asymptotes are lines, and you need to tell me which one's horizontal and which one's vertical. So the awesome thing about the stuff in the denominator is if you set it equal to 0, you're already solving for x. So you know that one's x equals something, and then the other one has to be y equals something. So let's use this information to make a graph. So to graph a rational function in the form a divided by x minus b plus c, when a equals 1, you can graph the asymptotes and then translate the parent function. So the parent function, remember, looks very boring, just something like this. However, if a doesn't equal 1, like this one here, we should make a table of values just to make sure that it looks the way that we think it does. So let's actually do b first. So the first thing you should do is find your asymptotes. This part right here tells me that x cannot equal negative 4. So that's one of my asymptotes. X equals negative 4. 1, 2, 3, 4. This vertical line that my graph cannot cross. And then this part right here tells me that y can never equal negative 2. So that's my other asymptote. And I won't use blue. Let's use black on this. So y equals negative 2 is right here. So these are the two lines that my graph can't cross. And because this is very similar to this equation, 1 over x, we know that it's just going to look similar to this. It's going to get really close to both of these on both sides. And we're done. The next one, though, it's a little tricky because it has 2 over something. That's going to change our values dramatically. The first thing we should do is the same, though. Find our asymptotes. So this right here tells me that x equals 3 is an asymptote. And since there's nothing being added or subtracted here, it's really 0. So that means y equals 0 is an asymptote, which is really just the x-axis. So now let's make a table of values to graph the rest of this. We know that we can't plug in 3, but we can plug in anything else. So if this is our x and this is our y, let's start with some 0, 1, and 2. We can't have 3, so skip 3. And then let's do 4, and 5, and 6. Plug those in and see what your values are for y, and then try graphing it and compare it with mine. So those points are the points I got, and because it's a rational function, I know it needs to resemble this shape over here. So because I have those dots on there and I know where the asymptotes are, I can just connect the dots. And it's going to end up looking almost exactly the same as the other one, especially because our graph isn't that exact. The whole table thing is just another way that you can graph them. But most of them are just going to look like translations of y equals 1 over x. So the very last problem is a story problem. I want you guys to do this on your own. And then when we come to class tomorrow, we'll go over it together. Okay? Have a good night.